It's time for some learning. Today, I want to talk about something that's on many of our minds, especially after the last few years. What does the future hold for our health? Specifically, what new diseases could emerge and impact humanity in the coming years? It's a heavy topic, I know, but looking ahead isn't about creating fear. It's about empowering ourselves with knowledge. Understanding the potential threats on the horizon is the first and most crucial step in preparing for them, protecting our families, and building a more resilient global community. The world is changing faster than ever before. Our climate, our technology, our very way of life is in constant flux. And with these changes come new challenges, particularly in the realm of public health. The line between human and animal habitats is blurring. Our medical defenses are being tested, and new technologies are emerging that carry both incredible promise and potential risk. Staying informed about these evolving health landscapes isn't just for scientists and doctors, it's for all of us. It allows us to make better decisions, advocate for smarter policies, and understand the why behind public health recommendations. In this video, we're going to take a clear-eyed look at some of the potential sources of new diseases. We'll explore everything from synthetic viruses and climate-driven illnesses to the growing threat of superbugs and even the risks posed by microplastics and artificial intelligence. My goal here is not to alarm you, but to arm you with information. By understanding what could be coming, we can collectively work towards a future where we are not just reacting to crises, but actively preventing them. So, let's dive in and explore what lies ahead for humanity's health. Let's start with a topic that sounds like it's straight out of science fiction, but is very much a part of our modern reality: synthetic biology. For decades, scientists have been developing incredible tools like CRISPR gene editing that allow them to manipulate and even create viruses from scratch in a laboratory. The primary purpose of this research is noble and vital. By building or modifying viruses, researchers can better understand how they infect cells, how they spread, and most importantly, how to develop effective vaccines and treatments against them. This work is fundamental to preventing future pandemics and fighting existing diseases like influenza or HIV. It's a powerful tool for good, helping us stay one step ahead of nature. However, this powerful technology represents a classic double-edged sword. With the ability to create comes the potential for error or misuse. An accidental release from a high-security lab, however unlikely, is a scenario that biosafety experts plan for constantly. A simple mistake, a contaminated sample, or a breach in protocol could theoretically lead to the exposure of a novel, lab-grown pathogen that human immune systems have never encountered. The very novelty that makes these viruses useful for study also makes them potentially dangerous if they escape the controlled environment of the laboratory. It's a risk that the scientific community takes incredibly seriously, with layers upon layers of safety measures in place to prevent such an event. Beyond accidents, there is the more sinister possibility of intentional misuse. As the technology becomes more accessible and the instructions for creating viruses more widespread, the risk that a state or non-state actor could use synthetic biology to create a bioweapon increases. This isn't just about recreating a known killer like smallpox. It's about the potential to design a pathogen with specific, dangerous traits. For example, one that is highly transmissible, but has a long incubation period. This is why international oversight, strict regulation, and a global consensus on the ethical use of this technology are more important than ever. The promise is immense, but we must manage the peril with equal gravity. The next major threat isn't born in a lab, it's a direct consequence of our changing planet. Zoonotic diseases, illnesses that jump from animals to humans, are not new. Rabies, influenza, and even COVID-19 are all examples. But climate change is dramatically increasing the frequency and likelihood of these spillover events. As global temperatures rise, ecosystems are thrown into chaos. Animals are forced to migrate from their traditional habitats in search of cooler temperatures, water, or food. This mass migration is breaking down the natural barriers that have historically kept certain animal species, and the unique viruses they carry, separate from one another and from us. Think about it this way. A bat species that once lived exclusively in a remote jungle might be forced to move closer to a suburban area, as its forest home becomes too hot and dry. This brings it into contact with livestock, domestic pets, and people, creating a brand new opportunity for a virus it carries to find a new host. Similarly, melting permafrost in the Arctic could potentially release ancient dormant viruses and bacteria that have been frozen for millennia. We have no idea what these microbes are, or what they could do if they were reawakened and introduced into modern ecosystems and human populations. The ecological disruption is a massive, uncontrolled experiment. Furthermore, changing weather patterns like increased rainfall and flooding in some areas create ideal breeding grounds for disease vectors like mosquitoes and ticks. This allows diseases such as dengue fever, Zika virus, and Lyme disease to expand into new geographic regions where populations have no prior immunity. Dengue fever, Zika virus, and Lyme disease. A mosquito-borne illness that was once confined to the tropics could find a new, permanent home in parts of Europe or North America. The connection is undeniable. A healthier planet is essential for human health. Addressing climate change is not just an environmental issue. It is one of the most critical public health imperatives of our time. For nearly a century, we have lived in the age of antibiotics, a miraculous era where a simple bacterial infection was no longer a death sentence. But our over-reliance and misuse of these wonder drugs have led us to a terrifying precipice: the rise of antibiotic-resistant superbugs. These are strains of bacteria, fungi, and other pathogens that have evolved to survive the very drugs we designed to kill them. Every time we use an antibiotic, we give bacteria a chance to adapt. The weakest are killed off, but the strongest, those with a random mutation that helps them resist the drug, survive and multiply. They pass on their resistant genes, creating entire populations of invincible microbes. This isn't a distant future threat. It's happening right now, in hospitals and communities all over the world. Infections like MRSA, drug-resistant tuberculosis, and carbapenem-resistant Enterobacteriaceae are already claiming hundreds of thousands of lives each year. Patients are enduring longer hospital stays, requiring more toxic and expensive alternative treatments, and facing higher mortality rates. Routine medical procedures that we take for granted, like joint replacements, C-sections, or chemotherapy, could become incredibly risky in a post-antibiotic world, as the danger of an untreatable secondary infection would be immense. The pipeline for new antibiotics, unfortunately, is running dry. Developing new drugs is scientifically difficult, expensive, and not as profitable for pharmaceutical companies as developing long-term medications for chronic conditions. This has created a perfect storm. The evolution of resistance is accelerating, while our development of new weapons is stalling. To combat this, we need a multi-pronged approach, better stewardship of the antibiotics we still have, meaning using them only when necessary. We also need massive investment in research and development for new types of treatments, like bacteriophage therapy or antivirulence drugs, to ensure we don't slide back into a pre-antibiotic dark age. We now turn to a threat that is as pervasive as it is tiny microplastics. These are minuscule plastic particles, less than 5 millimeters long, that have contaminated virtually every corner of our planet, from the deepest oceans to the highest mountains. They come from the breakdown of larger plastic items, from synthetic fibers shed by our clothing, and from microbeads in cosmetics. They are in the air we breathe, the water we drink, and the food we eat. Scientists have found these particles embedded deep within human lungs, in our bloodstreams, in the placentas of newborn babies, and even crossing the blood-brain barrier. We are, in essence, consuming and inhaling plastic every single day. The critical question that science is now racing to answer is, what is this doing to our bodies? The long-term health consequences of this constant exposure are largely unknown, creating a massive and concerning gap in our medical knowledge. Early research, however, is beginning to paint a worrying picture. These plastic particles aren't just inert specks. They can carry harmful chemicals on their surfaces, like pesticides or heavy metals, and deliver them directly into our tissues. The particles themselves may cause physical damage to cells, triggering chronic inflammation, which is a known driver of many diseases, including heart disease, diabetes, and even cancer. Furthermore, there is growing concern about how these plastics might disrupt our delicate internal systems. Could they interfere with our endocrine system, which regulates hormones? Could the accumulation of these foreign particles in our organs lead to new, as yet unnamed disorders, related to tissue damage or immune system dysfunction? We could be facing a future with a rise in inflammatory bowel diseases, reproductive issues, neurodegenerative disorders, or novel respiratory conditions, all linked back to this invisible plastic dust. Understanding the full scope of this threat requires urgent research, and more importantly, a global effort to drastically reduce plastic pollution at its source. Finally, we arrive at the most speculative, yet potentially paradigm-shifting threat, the use of artificial intelligence to engineer novel pathogens. AI is already revolutionizing medicine for good. Machine learning algorithms can analyze massive datasets to discover new drugs, predict disease outbreaks, and design better vaccines far faster than any human could. This same power, however, could be inverted and used for malicious purposes. An AI could be tasked not with finding a cure, but with designing the perfect pathogen. This is a frontier of bioterrorism that security experts are beginning to take very seriously. Imagine an AI system with access to all existing biological and virological data. It could be instructed to design a virus with a specific set of characteristics. For example, it could be programmed to create a pathogen that maximizes transmissibility while remaining asymptomatic for weeks, allowing it to spread silently and widely before anyone even knows it exists. It could be designed to target a specific genetic marker found only in a certain population, or to be resistant to all known antiviral drugs and vaccine platforms. The AI could run millions of simulations in a matter of hours, testing and refining its creation to be as effective and devastating as possible. This is no longer purely the realm of speculation. In 2022, a group of scientists demonstrated this risk in a thought experiment. They took an AI model normally used to find helpful new medicines, and with a few tweaks, tasked it with inventing new chemical weapons. In less than 6 hours, the AI generated 40,000 potential lethal molecules, including many that were more toxic than existing nerve agents. Applying this same principle to virology or bacteriology could open a Pandora's box of novel, highly sophisticated biological threats. Defending against this requires a new generation of biosecurity, focusing on AI ethics, regulating access to biological data, and developing AI-driven systems that can rapidly detect and design countermeasures for these new engineered diseases. We've covered some challenging and complex topics today, from synthetic viruses to AI-designed pathogens. The purpose, again, was not to leave you feeling fearful, but to underscore a vital truth. Our health is interconnected with the health of our planet, the ethics of our technology, and the strength of our global community. Staying informed is your first line of defense. I encourage you to follow reliable health news sources, listen to public health experts, and remain curious about the science that is shaping our future. Supporting scientific research, whether through advocacy or donations, is an investment in our collective survival. It's this research that will find the solutions to the problems we've discussed today. But our responsibility doesn't end with simply staying informed. It extends to our daily actions. The choices we make can help prevent future outbreaks. This means practicing good hygiene, getting vaccinated to reduce the burden on our healthcare systems, and being responsible with antibiotics. It means making sustainable choices to lessen our impact on the climate, which, as we've seen, is a major driver of new diseases. It means advocating for strong regulations and ethical oversight for powerful new technologies. A resilient future is built on a foundation of individual responsibility and collective action. Ultimately, the future is not something that just happens to us. It is something we build together. By fostering a culture of preparedness, awareness, and scientific literacy, we can face these emerging threats not with panic, but with purpose and resolve. We have the tools and the ingenuity to create a healthier, safer world for generations to come. It requires us to be vigilant, to be proactive, and to remember that we are all in this together. Thank you for joining me today to explore this crucial conversation. Stay safe and stay well.